Okay, we're going to look at some basic Java syntax here. And I think we'll start by comparing Java to what we already know, C++. And we'll see what's similar and what's different. Okay, so Java is similar to C++ in that we create classes. And we usually create one class for each logical entity. And we do this in object-oriented C++ programs as well. Also in Java, we have this idea of private data and public methods. We call this encapsulation, where this is where we hide the implementation details, the data and the algorithms, inside classes, and we provide a nice, friendly interface for people using the code. Okay. In Java, we also have this idea of association between objects. So for example, we might have a student class that we create many student objects with. Right? The class is the cookie cutter, and the objects are the cookies. So for each student object, we might want to associate some number of course objects. So we could create a course class and associate the student class and the course class together. These associations can be one-to-one, one-to-many, or many-to-many. In this case, a course can have many students, and a student can have many courses. Now, Java is different from C++ in a couple ways. The first is there are no pointers. Okay, so let's review kind of what a pointer is. Pointer is a variable that can hold the address of another variable. I can create a student object in C++. So here's my memory, and this might be some student object called student1. And it might have a first name, a last name, and a GPA, something like that. This object is going to occupy some location in memory. Okay, and right now it has a name, student1. I can also create this thing called a student pointer and assign it the address of the student object. And then I can use the pointer to refer to the student or dereference the pointer. So we could have this variable called pstudent, and it would hold the address of some object. So let's say this student object just happened to land at the physical address 1024. We could store the address of that object inside here. And the way I like to picture this is I like to picture the pointer actually pointing to an object. Okay, so why in the world would we want to do this? If you can create a student object, why not just use it and then skip this? Seems like an extra step of indirection. Well, in C++ programs, we have access to 3 different types of memory from which we can create variables. And pointers, the fact that we have to use pointers in some particular circumstances relates to one of these 3 different memory types. So let's review kind of the different types of data that we can have in a C++ program. We can have global data. So global data is accessible for the lifetime of the program and is accessible from anywhere in the program. There's no scope. Often, however, we only need data for short periods of time. Making a piece of data global means that it's going to be sitting in memory for long before it's needed and long after it will ever be used again. And memory is a precious resource, so typically we can't afford to misuse memory by storing everything in global variables. Now it's true that memory has gotten a lot bigger and a lot cheaper over the years, but we still have to worry about running out of our finite memory. Okay, we also don't want our data to be accessible from any and all points in a program. Okay, global data is accessible from any point in the program. It's generally better to limit which programmers can change certain pieces of data. This will reduce the likelihood of accidental or malicious altering of data. Right? So if I was a malicious person and I was writing code for maybe some bank, we wouldn't want to be able to do something like this. Right? So here the malicious programmer, Mark Mahoney, has in the code put this little condition here where if the account holder is me, basically I'm going to set my balance to $1 million. If account holder is global, this could happen. There's nothing really to prevent that from happening. Okay, so global data has its problems. The other type of data that we're probably all very familiar with is local data. So local data is accessible from the point of its declaration until the ending curly brace of the block the data was declared in. When a closing curly brace is encountered, all the variables that were declared in that block are removed from memory, and the compiler will ensure that you can't use that variable name outside of the block. That is, that variable has scope within the block. The limited scope of local variables remedies the problems associated with global data. So if we had something like this, we never need both y and z, so why set aside memory for both of them? Right? So why make y and z global variables if we know we're only going to use one of them? Also, y and z cannot be accessed by any programmer working on the program. Y and z have a limited scope, again, from the point of the declaration to the ending curly brace of the block it was declared in. Same with z here. We can only access it for a certain amount of time. Okay, so that brings us to our third type of data. We talked about global data, we talked about local data. There's a third type of data called dynamic data. So global data is totally unrestricted and can be used anywhere at any time. Local data has some pretty severe restrictions on where and when it can be used. Okay, the lifetime of dynamic data is controlled by the programmer. It springs into existence when the programmer wishes, and it is removed from memory when the programmer decides they don't need it anymore. All dynamic data is stored on a special section of memory called the heap. Okay, so you've seen me draw this picture many times. This is our RAM. We really have two sections of memory. We have something called the stack and the heap. The stack is where the local variables go, and the heap is where the dynamic variables go. Okay, so let's talk a little bit about what a program looks like when it's running. When a program is running, we call it a process. A process sits in memory and is managed by the operating system. Okay, so the operating system interleaves the execution of several programs over time. Okay, so if this is our memory, and let's say we have a couple different programs running, maybe Microsoft Word, maybe Chrome browser, and maybe the Eclipse IDE. Okay, each one of these we call a process image. And again, a process image just represents a running program. Okay, so like I said, the operating system interleaves the execution of these processes over time. However, it does this so fast that it appears that all the open programs on your machine are constantly running or concurrently running. But in reality, they're sharing one, or nowadays maybe more than one, processor at a time for a very short amount of time, just a little burst of time. A process image, okay, these sit in memory, can be broken into these different parts. If we were to examine this Microsoft Word process image in a little more detail, we'd see there's a data section, this thing called a text section, a stack, a heap, and this thing called a process control block. Okay? So every single program that's running on your machine has this process image somewhere in RAM. Okay, so let's look at these sections here. The data section of your process image, that's where all of your global data lives. Okay, so global data, remember, is available for the lifetime of the program. So when your process image starts, room is set aside for all your global data right in the data section. The text section of a process image, this is where the compiled machine instructions live. Right, so we talked about machine instructions in the last couple videos. The machine instructions are fed to the CPU by the operating system. So the operating system goes and finds these machine instructions in the text section. Okay, then we have the stack. Okay, this is where local variables go. Okay. And it's called a stack because it really is a stack, a last in, first out container. The stack is also used to control jumping to and returning from functions. We call it the call stack. And every time we call a function, we create this little thing called a stack frame. And any variables declared in that function will live in the stack frame. And if we call another function, that will get pushed on top of the topmost stack frame. Okay, then we have the heap. Okay, this is where dynamic variables go. And again, dynamic variables are controlled by us, the programmer. And then lastly, just to be complete here, we have this thing called a process control block. This is a place where we store information about the process. So for example, what is the current instruction, machine instruction that's being executed? And what is the state of the CPU's registers when it gets swapped out for some other program to run? We call that the process control block. Okay, so back to the question of why would we ever want to use this thing called a pointer? Well, it turns out the heap is made up of unnamed variables, since we, the programmer, are in charge of managing it. So the only way we can access data on the heap is with pointers. We can't ever give a name to a variable on the heap. Instead, we can just use the address of that chunk of memory. We can use it with a pointer. Okay, so remember, I can do something like this. Okay, what does this do? This creates a pointer. That's what the star means in C++, to an int. And it also creates a brand new integer on the heap, right, using the keyword new. I could do this with any type, so let's pretend I had a student type. If I wanted a student pointer, I'd say student star. And then pstudent is the name of the pointer. And when I call new, okay, what that means is go find room for a new student object on the heap and return the address of it to be stored inside this pointer called pstudent. Okay, so here we have pint, and when we say we want a new integer, we go and find some room on the heap, and pint refers to that piece of data. Here we have another pointer called pstudent, and we set it equal to the address of some student object on the heap. And again, this is how we manage our heap space. Okay, I also said that we are in charge of freeing up memory in C++, and we do that with a delete statement. Okay, so if I wanted to get rid of the memory associated with this integer here, okay, what I would do is I would say delete, and I'd give the name of the pointer that I wanted to free up. Okay, and what will happen here is we'll give up the memory associated with this data. So as soon as I said I wanted a new int here, it marked this as being used. Right? It's being used by this pointer here. Once I delete the pointer pint, this says delete the thing that pint points to, this chunk of memory is now marked as free and can be used for other dynamic allocations. Similarly, if we wanted to get rid of the student, we could say delete pStudent, and this means go to what pStudent points to and mark this as being free. Okay, so that memory could be used for other parts of the program. Okay, so what I'm saying here is Java has no pointers, and you might be thinking, oh, that's great, because all this pointer stuff is kind of confusing. Before you breathe a sigh of relief, though, let me make it clear that Java uses these things called references, which are essentially the exact same thing as a pointer. The only real difference is the syntax used to dereference or follow the pointer. So in C++, when you have a pointer to an object, you use the arrow operator to dereference a pointer. In Java, you use the dot. Right? So with my student object, for example, in C++, the arrow operator looks like this. Okay. What this says is go find the thing that pStudent points to, and the arrow here means select the data member called first name, and in this case, I'm assigning a value to that chunk of memory. Okay, so Java doesn't have pointers, but it has these things called references. Instead of an arrow, in Java we're going to use a dot. Okay, Java also has no memory leaks or dangling pointers. That's another difference between Java and C++. So in C++, several things can happen. Several bad things can happen. Let me take you through a few of these. Okay, so in C++, when we assign a 0 value to a pointer, that means that that pointer is a null pointer, or that it doesn't point to anything. In Java, we don't use the number 0. In Java, we have a keyword null. Okay, so one rule about pointers is if you have a null pointer, which pint is definitely a null pointer, it doesn't point to anything, and you try and dereference a null pointer, your program will crash. And that's kind of by design. We can prevent a certain type of error if we, as soon as we're done with a pointer, if we assign it a null value. Then if we accidentally ever use it in the future, the program will crash. Okay, so that's one thing that can happen. Another thing that could happen, we could maybe have similar code. Okay, here notice the only real difference is I didn't assign an initial value. Okay, so pint has a uninitialized garbage value, and the value is probably outside the range of the process image. Right, so remember these process images, they're all in memory here. If we have some pointer that refers to some other process image, The operating system actually protects your system by saying inside a process image you can only refer to other bits of memory that are within your process image. We can't have Microsoft Word interfering with the Chrome browser, right? So the operating system kind of puts boundaries around all these process images. Okay. And you can point to certain things within your own process image, but if you go outside the bounds of your process image, the operating system will kill your program. And that's a good thing. It protects poorly written code from interfering with well-written code. Okay, so that's an uninitialized variable. This will most likely, if we're lucky, cause the program to crash. If we're unlucky and it initializes to a value within the process image, the program might not crash, but it will probably not work correctly. Okay, another thing that can happen is we can have this thing called a memory leak. Okay, so here I'm creating a pointer and a new integer on the heap, and I'm assigning the address of that new integer to the pointer. And here I'm dereferencing the pointer. I'm saying go to what pint points to and store the value 10 there. Okay. And let's just say that this foo function ends right there. Well, we have a problem here. This is called a memory leak. Okay. Pint is a local variable, right? Pint is going to go away when we come to this ending curly brace. But pint is right now the only thing that points to that new chunk of memory that we just allocated. So the fact that pint goes away means we can never give that memory back. That's a bad thing. We could run out of memory if we called foo in a function or in a loop that executed, a million times or something. Every single time we call foo, we're leaking another integer, and we could eventually run out of memory. And the operating system will prevent a process image from consuming all the available system RAM. So at some point, the operating system says to a process image, "You're using too much RAM," and it will kill the program. Okay, so that's called a memory leak. We're really good at remembering to allocate data when we need it. We're not so good at remembering to deallocate it. So these memory leaks are actually pretty, they happen pretty frequently. Okay, the other thing that can go wrong, we could have this thing called a dangling pointer. Okay, so far so good. We're allocating this integer, we're using it, and then at some point in the future, we delete pint. We give the memory that we were using back to the system. Okay, this is exactly what I said we should be doing. Okay, but what might happen is, several lines down in the code, we might forget that pint doesn't belong to us anymore. So pint, we've given that memory back, but the pointer still holds the address of that chunk of memory. And if we dereference the pointer, that will definitely go and go to that address, whatever it is, and store the value 100 there. That's called a dangling pointer. It's a pointer that points to some memory on the heap, but that memory doesn't belong to us anymore. We've already given it back. Okay, so you shouldn't use dangling pointers because, like I said, you no longer control the data they point to. Okay, so we talked about memory leaks and dangling pointers. In Java, there are no memory leaks and there are no dangling pointers because we don't ever deallocate our data. So C++ programmers are notoriously bad at remembering to delete objects from the heap. We're really good at creating them when we need them, but often we forget to give them back after we no longer need them. So in Java we have this thing called a garbage collector. And this is a thread that runs in the background that frees up any objects that no longer have references pointing to them. So let me show you a little bit of Java code. Okay, we might be in some block here, and we might have a reference to a myDate object called bday. Okay, and we might do stuff with this. Again, bday is a pointer. And the object is over here on the heap. Okay, bday is the reference that points to the object on the heap. Okay, when we come to the ending curly brace, bday is marked for garbage collection. Right, because bday is a local variable, and whenever we come to the ending curly brace, the local variables go away. So when a local reference goes away, what Java does is it goes to that object that has a pointer pointing to it, and it basically keeps count. How many references are there that point to this thing? And if that number ever gets to 0, we kind of put a little check mark next to this thing, and we say this object in the future can be garbage collected. And like I said, the garbage collector is this low priority thread that runs when the JVM isn't terribly busy doing anything else. And it will go and it will clean up all of these objects for us. The garbage collector will free up those objects. You can call the garbage collector manually in your code by using the system object. So if you say system.gc, that will invoke the garbage collector. You might want to do that if you know for sure you're basically dumping a bunch of objects that you're never going to use again. Okay, so because the garbage collector handles cleaning up our data, we no longer have dangling pointers or memory leaks.